Hello everyone. In this chapter, chapter 12, rotation of a rigid body, we learn and understand the physics that involves rotation. So I've split this chapter into different small concepts so that you can have an understanding. So you need to understand the concepts involved and the quantities that are involved, whether the object is rotating at a constant speed or it is rotating at a constant angular acceleration. What is a rigid body? When we talk about a rigid body, we talk about an object that remains the same, or that has a shape and a size that remains the same, or that does not change. So a rigid body cannot be stretched, compressed, or deformed. All points on the body have the same angular velocity and the same angular acceleration. So you can see here this object, which is rotating on a parabolic trajectory or on a parabolic path. Let's consider a wheel that is rotating about a point here, x1. All points have a tangential velocity and a radial acceleration, which is called centripetal acceleration. They have a tangential acceleration if the wheel has angular acceleration. So the angular velocity is given as the change in angular displacement or per unit time, or it is the change in angular or the rate of change of angular displacement for a small change. Then we have angular acceleration, which is the rate of change of angular velocity. So we assume that the angular acceleration remains the same. So now to make calculations for the quantities that are involved in this motion, which is considered to be rotational kinematics, we use the equations of motions. So the first equation of motion, we have omega f, which is equal to initial omega plus alpha delta t. And the second one is this, and we also have the third one here. So we have angular acceleration, which is angular velocity, which is greater than 0, and angular acceleration, which is greater than 0 when the wheel is speeding up in a counterclockwise direction. Then we have the angular velocity, which is less than 0, and the angular acceleration, which is less than 0 for the wheel that is speeding up in a clockwise direction. So in these equations of motions, omega initial stands for initial angular velocity, which is measured in radians per second. Then omega final is the final angular velocity in radians per second. Then we have a theta there, which is angular displacement measured in radians. Then we have alpha there, which is angular acceleration in radians per second. Then we have delta t, which is the time taken in seconds. So we need to consider also this additional formulas. Tangential velocity is the same as the radius times the angular velocity. Tangential acceleration is the same as the product of the radius and the angular acceleration. Centripetal acceleration is the same as the product of the radius and the square of the omega, which is angular velocity, which is also the same as the square of the tangential velocity over the radius. So we have S, which is the same as the product of the radius and the angular displacement, which stands for the arc path or arc length. Let's consider here the wheel that is rotating with 2 points A and B. So 2 coins rotate on a turntable. Coin B is twice as far from the axis as coin A. So let's consider here the correct answer. Number A says the angular velocity of A is twice that of B. Number B says the angular velocity of A is equal to that of B. The angular velocity of A is half that of B. The correct answer here, of course, is B, because in a wheel, all the points, they rotate with the same angular velocity and the same angular acceleration. So the correct answer is B. The fan blade is speeding up. What are the signs of angular acceleration and the angular velocity? Number A, the angular velocity is positive and the angular acceleration is positive. Number B, the angular acceleration and the angular velocity is positive and the angular acceleration is negative. Number C, angular velocity is negative and the angular acceleration is positive. Number D, angular velocity is negative and the angular acceleration is negative. The correct answer is D, because when the object or the wheel is rotating clockwise, then the angular velocity and the angular acceleration are both negative. Number D is the correct answer. Okay, we need to take a note on this. When an object is rotating clockwise, the angular displacement, angular acceleration, and angular velocity are all negative. When an object is rotating counterclockwise, angular displacement, angular velocity, and angular acceleration are all positive. When the angular speed of the object is increasing, then the angular velocity and angular acceleration point in the same direction. When the angular speed is decreasing, the angular velocity and angular acceleration point in the opposite direction. You need to know that for us to use the rotational kinematics, then the angular acceleration should remain the same. Let's consider the first example here. It says a rotating wheel starts from rest to 12 radians per second in 2 seconds. Calculate the angular acceleration of the wheel. Okay, let's do this together. Example number 1. So what do we have? We have the initial angular acceleration, angular velocity, which is 0 radians per second, simply because the wheel is rotating from rest, which means initially it was stationary. So the initial angular velocity is 0. Then we have the time taken here, which is 0 seconds, which is time taken by the wheel to rotate from 0, which is initial angular velocity, to the final angular velocity. So we have the final angular velocity, which is 12 radians per second. So if the angular velocity is given in revolutions per second, you need to be able to convert it into radians per second. So what are we looking for? We're looking for the angular acceleration. Let's consider the formula here to use. So we can use this formula, the final angular velocity equal to the initial angular velocity plus angular acceleration times the time taken. So we are looking for the angular acceleration. We need to make it the subject of the formula before we make substitution. Then we're going to have angular velocity final minus the initial angular velocity divided by time. Then the second step is to make substitution. Where there is the final angular velocity, then we substitute it with 12 radians per second. It is very crucial to substitute the units so that you may see how they cancel each other. So this one is 0 radians per second. All over the time, substitute 2 seconds. Okay, let's punch the calculator together. So we have 12 radians per second divided by 2 seconds. So it gives us 6 radians per second squared. Okay, that is the answer. Please let's go back to our notes. An unconstrained object, for example, the one that is not constrained to rotate about a certain point there on which there is no net force, rotates about a point called the center of mass. Then the center of mass remains motionless while every other point in the object undergoes circular motion around it. Let's consider an object which is made up of particles. So we have particle I, which has a mass mi, which means if it is particle 1, mass is m1. If it's particle 2, then mass is m2, and so on. So the center of mass can be calculated as follows. So we can get, for example, the coordinates of the centroid, where we get the coordinates of x of the center of mass and the coordinates of y for the center of mass. So for nth or ith number of particles, then we have the coordinate of x, which is the same as 1 over m, where capital letter M stands for the sum of the mass of the individual particles, which is the sum times the product of the mass and the corresponding distance for the center of that particle. Then we get this. If it's only one particle, then we're going to have m1 times x1 over m1. If we have, which means the center of mass will be the same as the center of mass of that individual particle. If we have two particles, then we're going to have the center of mass for x, which is the same as m1 x1 plus m2 x2 over m1 plus m2. Then if we have three particles, it's going to be m1 times x1 plus m2 times x2 plus m3 times x3 over m1 plus m2 plus m3. So if we have nth particle, then we are going to follow, that's an example, up to the nth particle. If we have up to ith particle, then we follow the same rule up to the ith particle. We do the same thing with the coordinate of y for the center of mass. But now we'll replace x with y. Okay, so for example, yi, let's say if this particle is a particle yi, then it will be the distance from the x-axis up to the center of that particle, that is yi. So if this is particle 1, y1 will be the distance from the x-axis up to the center of that particle y1. So which means x, if this is particle 1, x1 will be the distance from the y-axis up to the center of that particle, which is particle 1. Then we can be able to calculate now the coordinates for the center of mass. Let's consider the second example here. It says a barbell consists of a 500-gram ball connected by a massless 50-centimeter long rod. So the first question, of course, is to determine the coordinates for the center of mass. So 2.2, we have to calculate the speed now of each ball if they rotate about the center of mass at 40 revolutions per minute. Okay, let's check what is given here. Of course, we're given the first mass, which is 2 kg. We're also given the second mass, which is 500 grams. We need to convert it into kilograms, so we divide 500 by 1000, then we get 0.5 grams. Okay, then we have here x1, which is the distance. We can take x-axis to pass through here, to pass through the center of these balls. Then we can take the y-axis to pass through the center of the first ball. Okay, so which means x1 is going to be 0 meters. Then x2 is going to be the distance from the center of the first ball to the center of the second ball. So which means x2 is going to be, we convert 50 centimeters into meters by dividing 50 by 100, and then we get 0.5. So x2 is 0.5 meters, which is the distance from the y-axis up to the center of the second ball. So we'll get, because M1 is bigger, so we expect the center of course of mass to be closer to M1. Then we can estimate it somewhere there, closer to M1. But if these masses were identical, of course the center of mass was going to be in the middle of the balls. Okay, solutions. Let's get the solutions together. As you can see now, we have only 2 objects, so which means the coordinates of x for the center of mass is going to be m1 times x1 plus m2 x2 all over m1 plus m2. If the balls were 3, then we're going to have m1 times x1 plus m2 x2 plus m3 x3 over m1 plus m2 plus m3. But now we are limited only into 2 balls. So this is how our formula looks like. And then the second step, of course, is to make a substitution. So where there is M1, of course, we're going to put 2 kg. Then where there is X1, of course, we're going to put a 0 there. And where there is M2, we're going to put M2, which is 0.5. Where there is X2, we put X2, which is 0.5 meters. Where there is M1, we put 2 kg. Where there is M2, we put 0.5 kg. Then let's substitute. So we have our substitution here. Then let's punch our calculators to get the answer. So the best, of course, is to substitute the units as well, so that you can see how they cancel, so that you can get also the unit of the quantity that you're looking for correct. Also, for example, it shows you if you forget to convert the distance from 50 centimeters to meters, then when you cancel your units, you see where you went wrong. Then you can be able to always go back and converted the units into the correct unit. So also the same thing with the second mass. If you didn't convert it into grams, you'll see that a kilogram and a gram, like they don't add, then you'll have to convert it. Okay, so the final answer is 0.10 meters, which is the center of mass. Okay, that is for the coordinate of x, so we can do the same thing for the coordinates of y. So now for y, as we have mentioned, that y and x-axis, they pass through the origin, which is the center of the first mass. So which means y, the center of mass, or the coordinate of the center of mass for y, is of course 0. Okay, now 2.2. So what we do now, we convert the angular velocity, which is given in revolutions per minute. So we know that 1 revolution is equivalent to 2 pi in radians. Then we convert it into 2 pi. We know that minute is equivalent to 60 seconds. Then this is how we convert a revolution into radians. And then we get the answer there of 4.19 radians per second. Okay, so the radius of the first is of course going to be 0.10 meters. How do we get it? Because it's going to rotate around the center of mass, which forms a radius. So now from the center of the first object to the center of mass, of course, the radius there is 0.1. So now to get the radius for the second one, so we subtract now 0.1 from 0.5. Then we get the radius of R2. So which means this one also is rotating about the center of mass. So then the radius is 0.4 meters. Okay, now to get the angular speed for the first object, of course, we use this formula, which is r the radius times the angular velocity. Then we make substitution there, we get the answer, which is 0.42 meters per second. Then the same thing with the V2, we get R2 times the angular velocity, which is 0.4 times 4.15 radians per second. Then we get 1.68 meters per second. So this gives us tangential speed of those two balls. Okay, let's go now to the tutorial problem number 1. We have a rotating wheel which starts from rest to 12 radians per second in 2 seconds. So now we need to calculate the angular acceleration of the wheel if the wheel speed, we want it after 8 seconds. Okay, so here we need to calculate, we calculate the angular speed. Okay, so the tutorial problem number 2. So we have a barbell which consists of 500-gram ball connected by a 50-centimeter long rod. The mass of the rod is 800 grams. So 2.1, we need to determine the coordinates for the center of mass. 2.2, we need to calculate the speed of each ball if they rotate about the center of mass at 40 revolutions per minute. So now the rod here has a mass, it is not massless. Okay, that is the end of the lessons. Thank you for taking part. All the best. Thank you.